Hello, can you repeat?
3A, most of the alpha particle go straight through. Why?
Because it didn't just like deflect from the nucleus or maybe bounce off on the nucleus.
No, this one, this one,
Yeah,
this
3A,
one.
right? Oh, okay. I thought
Most of the
it's
alpha
like
particle go straight through. Well, how do the force model explain it?
isn't it like that?
Huh?
Isn't it like that? Because
Say again?
when it goes because some of the alpha particles they just like bounce off from the nucleus, right?
No, nucleus is very small.
Yeah,
Nucleus is in an atom. The nucleus is very small. So most of the
yeah.
alpha particle will have missed it. It doesn't come under the influence of the positive nucleus. So that's why it goes straight through. Okay?
Oh, okay. So okay. So most of them will not just like have contact with the nucleus lah.
Nucleus extremely small.
Okay.
So most of the alpha particle doesn't come near the nucleus at all. That's why it goes straight through. Okay?
Okay.
We
Okay.
just now we look at the size of the atom. Atom is 10 to the power minus 10 meter. The nucleus is 10 to the power minus 15 meter. Very small. Imagine in a huge room, and then the nucleus is just an orange in the middle of the room. You throw ball, which is alpha particle, most of it will go straight through without hitting the nucleus. Okay, some alpha particles are deflected at large angle. This one,
Because they bounce off the nucleus.
it doesn't bounce off the nucleus. Right? It comes near the nucleus, it's deflected.
Yeah, but because the explanation over there wrote like this, it's like it bounce off the nucleus.
It didn't bounce off, This one is bounce off. This one it come too near the nucleus, that's why it's deflected. This one also come too near the nucleus, that's why it's deflected. So it depends. If it come nearer, it deflected more. If it's further away, it deflected less.
Oh, okay.
Right? Only this one bounce off. Right? Where it hits the nucleus directly, then it bounce off.
So it is different with deflected at large angles lah.
Deflected is this one. At
Yeah,
large
but large
angle.
angles.
This one not
Oh,
deflected.
okay.
Most of it are not deflected like A.
Okay.
Right? Repelled by the positively charged nucleus. Right? It come too close, so it get repelled. It just changed its path at all. Why do the result of the experiment on the right suggest that the nucleus has a positive charge? Can
Um, is it because that the alpha particles are negative?
yeah, this one is it come too near the nucleus, so it's repelled. The path is changed. This one is more hitting the nucleus. Right? So the nucleus is very
Okay.
small, massive nucleus, very small.
Yeah, I
And
know. Does it
compared to
mean
the
like
atom there, it's very small. Right? So alpha are positive and are repelled by light charges of the nucleus. Okay?
okay? Because not that clear about the topic about this experiment.
Right? This diagram is very poor. Between this is the nucleus, this is the orbit of the electron. Right? More like valence shell. Right? But this nucleus is very small. Right? From one nucleus to another nucleus, a lot of space there. So that's why a lot of these are going straight through like A. Right? Remember, positive charge and positive charge repel. This is where it comes to close the nucleus. The positive and positive charge repel. So the direction changes only. Same like here. Yeah, it come too close there, so it repel, change direction. Whereas this one, direct hit, so it rebounds back. That's why we find very few this type, because the nucleus is very small. Okay, now what's the problem? Okay, no.
Okay. Just the alpha particles itself is negative or positive?
Positively charged. It has
Positively
lost 2
charged. Okay.
electrons.
Okay.
So positive and positive charge repel. So instead of it going in a straight line, it comes too close, it gets repel. But it's still moving in its own straight line. But it's just deflected.
Oh.
We call deflected. Right? This is deflected.
Okay. So it means like because both are positive, so it repels or deflects, right?
It repel each other.
Okay.
So it repel each other means it gets deflected.
Okay.
It change direction. If the nucleus is not charged, then the alpha particle will go straight through without change of direction. Can?
Yes.
Okay or not?
Yes.
Okay, then we carry on. Right? This talk will summarize for you what we did just now lah.
Here's a question for us to look at. So let's start by reading through the text in the question and then answering the question. A nucleus of helium has the symbol He32. Complete the diagram to show an atom of helium using P for protons, N for neutrons, and E for electrons. And we haven't been given any clues because it could be one proton or many, one neutron or many, and one electron or many. So let's just highlight what we have to do here. So we just have to complete the diagram. So we've got these positions here, and we need to fill these with P's for protons, N's for neutrons, and E's for electrons. So as a starting point, let's just remind ourselves of a model of the atom. This is often referred to as the Bohr model of the atom, after the scientist Niels Bohr. But we've got protons and neutrons in red and green, as shown there, and they make up the nucleus. And then we have these much smaller and very much lighter electrons, and they are to be found around the nucleus, relatively far away from the nucleus, and notionally we say that they are orbiting the nucleus. So we can start, I think, with the electrons. That's probably a good place to start because it's quite clear where they are. So let's go for it. So the electrons are located, and I've put orbits in inverted commas there because it's not quite as simple as that. But for the purposes of this course, we will just say that they're in orbits around the nucleus. So in the case of helium, we've got the 2 electrons there and there. The next part is the neutrons and the protons, and that means we need to understand what these numbers here, so the 3, 2 with the He for helium, what does the 3 mean and what does the 2 mean? So just as a reminder of that particular piece of the theory is, and this is the example of lithium, the number at the top is called the nucleon number, and the number at the bottom is called the proton number. So let's focus on the proton number. So lithium, the proton number is 3. We're not worried about lithium, we're worried about helium, and the number at the bottom is 2, which means that we know that the proton number for helium is 2, which means there has to be 2 protons in the nucleus. So we can go and fill those in. The number at the top is called the nucleon number, and the nucleon number is the total number of protons and neutrons in the nucleus. So we've got 3 particles in the nucleus. That's what the 3 over there stands for. 2 of them are protons, so the last one has to be the neutron. So that's the complete picture of an atom of helium.
Okay, any question you want to ask before we carry on with our new topic?
No,
No,
no
okay.
questions.
Okay, let's carry on. What is happening? Proton, neutron, and electron. Table of relative charge and mass. Relative charge for proton is +1. Neutron no charge, so it's 0. Electron is -1. Relative mass of proton is 1. Relative mass of neutron is also 1. And relative mass of electron is about 1,200 times smaller than the mass of a neutron or proton. So usually we call it negligible. Negligible. That means it's close to 0 lah. Different particles that make up the atom have different properties. Relative mass is a way of comparing particles. Relative mass is to compare. It's a measure of the atomic mass unit. Some use AMU or U. This is for your info only lah. You don't need to know that much. Only in A level you need to know more than that lah. So the relative mass of 1 is equal to 1.67 times 10 to the power minus 27 kilogram. Okay, it's for your info. Charge can be positive or negative. Relative charge, again, used to compare particles. Fundamental charge is equal to the size of a charge on a proton or electron. Usually we call it the charge of the electron. However, the electron charge is negative. Properties of each of the particles are shown on the table. We have just gone over with you the table. If the particle has 0 relative charge, it means it's neutral. Both proton and neutron has a relative mass of 1. This means they have the same mass. Roughly the same mass. To you, you just say it's the same mass. Nuclear charge is usually stated as a relative charge of the nucleus. The term relative refers to the charge of the particle divided by the charge of proton. Proton number is the number of protons in the nucleus. Since nuclei are made up of only proton and neutron, the proton determines the relative charge on the nucleus. Okay, try this question. What is the relative charge of the chromium nucleus? Yep. Relative charge of the chromium nucleus.
Just now it say it's like the charge of the particular particle divide by the proton number, right? The charge of the proton.
The charge on the proton.
Can you tell me how?
Just
It's like
24.
the formula.
Relative charge 24 electron, standard 24. If you want to know the actual charge, you just times your charge on the electron or charge on a proton. So 24. Can or not?
cannot because I don't know how to calculate in
You just
method.
read that. If you say relative mass, you just read that, lor. Relative mass, relative mass. No need to put kilogram or what, because you compare it to the mass of a proton or neutron.
Oh, okay, okay.
Relative charge you compare to the electron or proton.
Okay.
Can?
So it is normal. It can say that just like name the charge of the nucleus
Instead
like
of
that, right?
multiplying by the charge of a proton, which is very small number, we use relative charge. We compare the proton. So you have that proton number is roughly the same as your relative charge. And your relative mass is same as your nuclear number. That's why we call mass number. Okay,
Okay. Can already. I know already.
charge can be positive or negative. Therefore, remember to include the sign when writing relative charge. Nuclear mass is stated as the relative mass of the nucleus. Right? Rather than multiply it out, we just want an approximate mass. So the nuclear number is roughly the nuclear mass. So the term nuclear, the term relative refers to the mass of the particle divided by the mass of proton. Right? So basically, relative mass is just that. Later on, will give you relative charge. Mass number is the total number of proton and neutron in a nucleus. Nuclear number, right, or mass number determines the relative mass of the nucleus. What is the relative mass of chromium nucleus?
The relative mass it would be 52, right?
Ah,
52,
good.
52.
That's all. Just instead of calling it mass number, you call it relative mass. If you want to find the actual mass, then you have to multiply by the mass of a proton. Okay, if you are all right, we carry on. 52 is the correct answer. Relative mass of nucleus only includes protons and neutrons. However, this is pretty much the relative mass of the whole atom because electrons have negligible or very little mass in comparison with the proton and neutron. Okay, try this question. An atom contains electron, proton, and neutron. This is page 227 in your book. Which of these particles are outside the nucleus?
Electrons.
Okay, good. Uncharged?
Neutrons.
Okay, good.
Electrons for
And
C, and
negative
then
charge?
electrons.
Good. Are nucleons?
Protons and neutrons.
Good. Are much lighter than the others?
Electrons.
Good. Can remember that? Good. An aluminum atom has a atomic number of 13 and a mass number of 27. How many protons are there?
A and B are also 13, and then neutrons is 14.
How many neutrons?
14 neutrons.
14. How many electron and
Yes.
proton?
13.
Okay, good. That's all. Chlorine is a mixture of two isotopes with mass number 35 and 37. What's the difference between the two types of atom?
The number of protons.
Number of what?
Protons.
No. The proton is the
No,
same.
no, it's the neutrons.
Good. Number of neutron. Different number of neutron. Symbol. In symbol form, nitrogen 14 can be written as that. How can each of the following be written?
For A, it will be 6, 12, C. B, it will be, 14, 6. Wait, A is 12, 6, C, and then B will be 16, and then 8, O. C will be 226, and then 88, RA.
Make sure you know how to write all these symbols there. Atom X has 6 electrons and a mass number of 12. Atom Y has 6 electrons and a mass number of 14. Atom Z has 7 neutrons and a mass number of 14. Identify the element X, Y, Z. What is X?
X is carbon,
Carbon, okay.
and then
Y?
Y is also carbon isotope,
Isotope of carbon, okay.
and then
Z?
iron and also isotope of carbon.
Isotope of what?
Wait. No. It's not like that. Not like that. Let me think. Nitrogen. Nitrogen.
Are you sure?
Nitrogen. Um. Yeah, I'm sure.
Okay, yeah, sure, okay. Nitrogen, right? 7 neutrons, so it means there are 7 protons. So 7 protons, you look at the table, 7 protons. Okay, good, let's carry on. This is page 236, right? Fission and fusion. Fission and fusion, right? This is a neutron, this uranium-235. So when you send a neutron in, they combine and then they break into 2 smaller atoms. These are called nuclide, daughter nuclide, right? Plural for nucleus. And these are 2 or it can be 2 or can be 3 neutrons. Right? So we got nuclear fission. There's a lot of energy stored within the nucleus of an atom. Energy can be released in a nuclear reaction such as fission. Right? So when this happens, energy is released. So besides there are 2 daughter there, and then 2 or 3 neutrons. Nuclear fission is defined as splitting of a large unstable nucleus into smaller nuclei. Right? This one need to memorize. Isotopes of uranium and thorium both undergo fission and are used as fuel in nuclear power stations. During fission, when a neutron, that's a neutron, collide with an unstable nucleus, this is the unstable nucleus. The nucleus split into two, smaller nuclei, these 2 are smaller than this one, and we call it daughter nuclei, as well as 2, this can be 2, it can be 3, right? It depends on what is these 2 come out to be. And then gamma ray are also emitted. Nuclear fission, the product of fission move away quickly, right? Because they have energy, they have kinetic energy, they move away. Energy transfer from nuclear potential energy, despite nuclear potential energy, a lot of energy inside, despite moving away, so it's kinetic energy. So nuclear potential energy converted into kinetic energy. Mass of product, these are the mass of product. Add all of them up. Daughter nuclei and neutrons, add all of these up, is less than the mass of the original nucleus. If you add these 2 together, these two have a greater mass than all these masses. This is because the remaining mass has been converted into energy, which is released during the fission process, right? So this mass is greater than all this mass. The difference in mass appears as energy that's released. The process involved in nuclear fission can be shown in different ways as a diagram. I can show you in a diagram. This diagram shows how the reaction takes place in a way that's easy to understand. Diagram is easy to understand. Diagram is useful because it shows clearly the different parts of the fission reaction. Right? Diagram there show you what's happening. An example of nuclide equation. So we have to write a nuclide equation. That's a nuclide equation. That's a uranium, and then you send a neutron in. Right? This side there is the left-hand side. Okay, we will have to end in 5 minutes time. Then this is the fission product. One of them is Proton.
Excuse me.
One of them is beryllium. And then you got 3
Excuse me.
neutrons.
Yes, please,
Okay,
sir.
so
Excuse
that is
me.
your nuclide notation equation.
Sir, excuse me.
Say again.
So, excuse me, it's like overall, nuclear fission is the idea when one atom, or just like atom like that, it got divided into two, right?
Usually this is a neutron. And then this is
Yeah.
unstable. So the neutron causes
Yes.
it to split into two smaller ones. No? Idea is this is a big one, split into smaller one. And
okay. So
you have 2 or 3
so
neutrons.
so the idea is like one neutron, it get contact with one unstable nucleus, and then this lead to the like division of two new daughter nucleus like that, right?
Basically, it is already unstable. So
Yeah.
this neutron give it extra energy. So unstable, you want to give out its energy. So it's split into two smaller one. No? Smaller one, daughter nucleus, daughter nuclei, and then it also give out 2 or 3 neutrons. No? Okay with that?
Okay, thank you, sir. Yeah, I'm okay with it. Okay with it.
All right. So that is your nuclear equation. You should know how to write that. Right. So that's the other side. So that is the product. This is the reaction, and then it's energy given out. So they stop there. Right. 235 plus 1 must be equal to 92 plus 1 for 1. There is 3 neutrons. So 3 times 1 is 3. Okay. So these two sides must be the same. Left-hand side must equal to right-hand side. Right. We call it conservation of nucleon. No? Right. It's also true of this part, 92 plus 0. Right. This is the charges. The charges must be conserved. That means the charges must be conserved. Cannot lose any charge. So 92 plus 0, 92 plus 0, 36 plus 56 plus 3 times 0 is 0. Okay, so 3, not 2, sorry. Can? Any comment?
No comment.
Okay, if not, let's finish it off. We have not much time left. Right, this is called conservation of nuclear number. This is called conservation of charge. Right, this is for info only lah. Right, as I said, textbook put extra info for those students who are curious, where is the users there. So that this is called a change reaction lah. This one neutron collide with the unstable nucleus, produce two neutron, and that neutron hit another nucleus, produce another 2 neutrons. So this continue on. A lot of energy is produced up. So if you don't control it, it will be a explosion. So in a nuclear reactor, to produce electricity is control, right? You control in the reactor. Then it produces steam, and then it generates electricity. Okay, so I will stop here. Next Saturday, we will carry on with nuclear fusion. Any question that you want to ask?
No question.
So you can try. You can try page 237. Right? Mainly number 5 lah. The others you can try just for extra knowledge lah. You read your textbook and then you can try it out. I'll go over with you the answer. So if no question, we'll stop here. Okay with you?
Okay, thank you, sir.
Any more question? If not, we'll stop here.
No question.
Okay, good night then. See you
Thank you,
next
sir.
Saturday.